I looked at it in different angles, and I started to think, well, okay, so if I'm not dealing with just one tetrahedron, then there must be the interaction of the tetrahedrons may have different geometries involved in it. And since I was really investigating the structure of the vacuum, I was very interested in the negative space between the tetrahedrons. So I eliminated the tetrahedrons from the space and extrapolated what was in the middle of it, in between the tetrahedrons. And what I found is that what's in between the tetrahedrons is octahedrons, right? Now, an octahedron is a double bonded pyramid, okay? Emphasis on the word pyramid. This is the cavity between the tetrahedrons of the isotropic vector metric. Can everybody see them there? They're tilted like this, okay? And you could think of, for instance, if we look at this top one of the points of the pyramid is up here, the other point is back here somewhere, and it's on an angle somewhat like this, right? For you guys to look at. Everybody sees that? Oh, not quite, like this, right? Okay, so I was excited. Oh, here's the pyramids. It kind of linked with the ancient concepts. Okay, well, that's interesting. And then as I kind of traced all the vectors of the pyramid and in my drawings and in my head, I didn't have a computer at the time. I realized there was some strange negative cavities inside the isotropic vector metric. So here's our isotropic vector metric, and here's the cavities that I noticed that were inside it. Now, if there's 20, so let's put it this way, and if we look in between, there's our octahedrons, okay? But in red here, we've demarked that actually there is another set of tetrahedrons in the middle that are pointing inward, that are pointing down, right? And that are rotated from the initial metric. When I found those, I was surprised because this is thought to be an isotropic vector metric. I thought that must be the same everywhere. There shouldn't be any asymmetry. And certainly, I was looking for the geometry of the vacuum, so I was certainly looking for something that was in equilibrium and couldn't have asymmetry in it. So I was surprised. I didn't know what to do with these cavities in the middle. They didn't belong to the octahedrons, and they didn't belong to the tetrahedrons that were pointing up. So I thought, well, there's one thing for sure, is that if the universe is polarized, it cannot be that the geometry of space would have only one polarity of the equation. It would have to have both sides of the equation, and I had to add the reverse metric to it to get the polarity, the male, the female, the plus, the minus, the white, the black, and so on. So I added another metric below it, but when I did so, if I put one metric base to base to the other, if I put another one base to base to this one, then I have another problem. And that is, I don't get a sphere. I get an egg-shaped structure. And I was looking for the sphere. So this was like a chicken and an egg problem, and I was very confused. I was spending a lot of time on this. I'm walking you through things that took years because I was working to survive at the same time. Eventually I quit my job, sold all my ski equipment so I could move into a van and sponsor my own research with very little cost. And so I was in my van thinking about all this. I didn't have a computer. So I've got these matrices in my head spinning, and I'm doing all this stuff with them. And I don't want to distort the geometry of the metrics. I'm not wanting to push them into each other. So I'm resisting that idea, and I'm trying to figure out how they would work. And then eventually, I came to it. I did push one into the other, which took me a while because I had to render all these vectors in my head. And I realized that when they would be in perfect relationship to each other, then I would get a perfect sphere. However, what got me extremely excited is that when I pushed one into the other and rotated so that it would be in perfect polarization to each other, the central red space that I didn't know were for what were exactly in the right position to accept the reverse metric without having me distort the geometry or remove tetrahedrons or anything like that. So that the polarized metric would actually be incomplete without its better half. And that when the second metric was inserted into it, it would take exactly the spot to create perfect symmetry at the center. And I was really excited because I was looking for perfect symmetry equilibrium. So I started to render in my head what is the geometry of these tetrahedrons coming in the middle. And that's when I realized that the result of the two metric intersecting with each other to create the perfect sphere generated in the middle what is called a cuboctahedron, which is 8 tetrahedron coming together, which was called by Buckminster Fuller the vector equilibrium. The only geometry in which all vectors are in equal proportion to generate perfect equilibrium. I had found the geometry of perfect equilibrium from the polarity of the two isotropic vector metrics coming together. Why is this geometry, for instance, the only geometry that's in perfect equilibrium? Well, I studied a little bit and I realized that actually, if you have vectors of forces and you want to create equilibrium, then you would have, obviously, now, this vector that just popped out could express a force. And we'd say that that force has this specific unit which relates to the length of the vector. So bigger the vector, stronger the force, smaller the vector, smaller the force. If you wanted equilibrium, you'd send another vector in the exact opposite direction, at the exact same length, and you'd get equilibrium. However, this would be a very precarious equilibrium. Nature could not use that equilibrium because any distortion would make the vector collapse. Any forces in any other direction would break the equilibrium. So it was very unlikely that the universe used that type of equilibrium. Well, what would it do? Because this is unstable. What would it do? Well, if you were trying to get an equilibrium yourself, you would probably say, well, I'll just keep adding vectors. Well, if you add vectors at 90-degree angle from the initial vectors, you're still not going to get equilibrium because now what's going on is that the edge vectors are longer than the vectors to the center, so they're stronger, it implodes, it doesn't work. No equilibrium. So what would you do? You probably continue to add vectors, and you would probably put them at 45 degrees from the initial one. And now you have another problem. That is, the edge vectors are shorter than the vectors to the center. Now the geometry explodes. Is still no equilibrium. So what would happen is that you would have to make sure that the geometry's edge vector and vectors to the center are the same length. And the only geometry in which has to be, like the snow crystals, the hexagon, where the edge vectors are the exact same length as the vectors to the center, And if we made a 3D hexagon together, we would get a vector equilibrium, which is made out of 12 vectors radiating from the center and 12 edge-bounded vectors that maintains the structure in perfect equilibrium, or 8 tetrahedrons coming together, all right, to create, you know, a vector equilibrium. So 8 of these coming together to create a vector equilibrium.